Hello, my name is Daniel Kinsley. Today I'll be talking about analyzing Bitcoin price changes with Storm. So Bitcoin is a decentralized currency. It's just like dollars or euros, except it's not controlled by a central government. Um, the recent rise in popularity has caused the market to fluctuate wildly. For example, one day in April, the price skyrocketed to $250, only to plummet back the next day. And because of this extreme volatility, it's easy to miss an opportunity to sell high or to buy low. And as an armchair trader, I don't want to be burdened by following the market during the course of the day and potentially miss opportunities. So I need a system that can track the price and send alerts if there are major price fluctuations. So in order to solve this problem, I decided to use Storm to process the Bitcoin ticker information in real time. It was created by an engineer at Twitter to process the Twitter firehose and develop analytics against it, such as the trending function. The creator says that Storm is doing for real-time processing what Hadoop did for batch processing. Storm can be used as an ETL engine to pre-process data before loading into Cassandra or a traditional database or data warehouse. It can be used for distributed low-latency remote procedure calls, or for continuously running MapReduce functions. But with that said, it's important to note that Storm is not meant to replace Hadoop, yet rather serve as another tool in the Big Data Engineer's toolkit. So why don't we take a look at where Storm fits into the complete big data architecture. So the batch layer would consist of Hadoop, HDFS, Hive. It performs all of your offline processes. So the serving layer takes the data refined by the batch layer, the MapReduce outputs, and it structures it in a manner that's digestible by end user applications. So this is something like MySQL, Teradata, Cassandra, ElephantDB, something that's good for high concurrency. Now, where Storm lives is in the speed layer. So it fills the gap between immediately after an event occurs and when your batch process completes its analysis of the data and pushes it to the serving layer. So the union of the serving layer and the speed layer results in a complete up-to-the-second view of your entire data set. So every couple of hours, as the batch layer pushes new data to the serving layer, the result is that the old data is no longer required to be kept in Storm, so it can be discarded. So Storm, by keeping the most recent data, can be really fast and not have to worry about past historical data. So now we know where Storm fits in our architecture. Let's take a look at how it actually works. So one of the greatest features of Storm is how it's completely distributed. Scaling out is as simple as adding new nodes to the cluster. So tasks or jobs in Storm are called topologies. Topologies are similar to a MapReduce job in Hadoop. And to continue with this analogy, the Nimbus node is similar to the Hadoop job tracker. So you submit topologies to the master, and it's distributed across any number of the supervisor worker nodes. And members of the cluster and various other state information is maintained in Zookeeper. So if a node dies, the state's updated in Zookeeper, and tasks are redistributed accordingly. And on top of all that, there's a UI, so you can view the running topologies, see the errors, latency for a tuple to traverse the entire topology, etc. So a Storm cluster can run any number of topologies. A topology processes streams of data that are produced by spouts. So a spout can be anything. This can be an API like the Twitter firehose, a message queue like Kafka, Kestrel, RabbitMQ. For my project, I made a spout that connects to the Bitcoin exchange web API and then emits tuples for every tick. So bolts connect to these spouts of data, and they perform some function on the tuples. So bolts may also emit further tuples. to be used downstream. Or it may just be the end of the processing, and you could persist it to a database like Cassandra or Hadoop, etc. For this project, I created a bolt that calculates aggregate statistics of a value over a rolling period. So now that we know a little about how Storm works, let's dig into how I use Storm to alert me if the price changes. So we start with two spouts, which are two instances of the polling Bitcoin ticker spout. So the spout will simply emit the current price of Bitcoin on that exchange. So these two spouts are connected to the price counter bolt, which is instantiated to keep a 1 hour rolling history and emit the statistics every 30 seconds. So the summary bolt calculates the price delta and will alert if necessary. You can see that the last parameter in all of these setters is how many threads to invoke. You can see we set this to 1 in these examples, but I can easily set this to 2, 3, 8, however much concurrency I need for my topology. We can also see that the price counter bolt, I use the fields grouping on exchange so that all the tuples from the same exchange will always go to the same thread. And this is one of the key components that makes Storm so scalable. For example, if my application had dozens of threads and each thread maintained a cache of some field, I'll get a much higher hit percentage by sending the field to the same thread each time rather than a random thread. And there are other groupings such as shuffle grouping, so it'll send it to a random thread. All grouping, which sends the tuple to every thread downstream, or global, which sends it to a single thread. Let's take a deeper look at the spout that I created. It's very straightforward. All it does is connect to a public API, retrieves the last price, the bid, which is the maximum amount someone is willing to buy a Bitcoin for, the ask, which is the minimum someone is willing to sell it for, and the volume of transactions. So then it emits the tuple, so any bolts that are connected to it can process it. Since this is a public API, the spout will sleep for 10 seconds so it doesn't DDoS it. In the lower part of the slide, we can see the output produced by this spout. So the rolling price bolt, this is where the magic happens. So as tuples are emitted from the spout, the rolling price bolt will maintain aggregate statistics for each combination of exchange, so Mt. Gox or Bitstamp, and the values, so bid, ask, last, and volume. So the bolt is configured with two parameters: the window length, which is the number of seconds of history to consider, and the emit frequency, which is how often we want to emit a tuple containing the aggregate statistics for each metric. The secret to maintaining the rolling window is by breaking the window length into distinct slices. So for a rolling window of X seconds and an update frequency of Y seconds, the bolt will maintain an array of X divided by Y elements containing statistics for every Y period. So every Y seconds, a tuple will be emitted that iterates the X divided by Y elements of an array, calculates the aggregate statistics over the rolling window. That's pretty confusing. Let's break it down with an example. So let's say we wanted to calculate statistics for the past 2 minutes, and we want to be updated every 30 seconds. To do this, we create an array with 4 elements. In the first 30-second window, we process all incoming tuples, and we update the head element with the minimum, maximum, average, and sum for all the tuples that we received in this 30-second period. So at the end of the period, we set the tail element to be the head element, and then we repeat the process, loading the statistics into the new head element. So essentially, we've created a ring so that we're replacing the oldest 30-second window with the newest 30-second window. And to calculate the total statistics of the rolling period that you're interested in, all we need to do is iterate over each slot, and we choose the maximum of the maximum in each slot, the minimum of the minimums in each slot, etc. And so we package these aggregate statistics up, and then we emit the tuple to bolts downstream. Now let's say, for example, we wanted to change our window to a rolling 3 minutes and keep the 30-second emit interval the same. In this case, we would have 6 buckets, so it would be 3 minutes divided by 30. And now that we have our statistics calculated, all we need to do now is just look at these tuples incoming, subtract the maximum from the minimum, and this is our delta. It will take the absolute value, and then if it's greater than 5, we send an email alert. This is pretty straightforward. So one of the great things about Storm is how easy it is to develop against. You can run an entire topology 100% within Eclipse. So you can make changes quickly. You can test on your machine without having to touch the production hardware. And so when it's ready, you just create the jar file and then submit it to your production cluster. I think this is a huge advantage over Hadoop. Developing against Hadoop in Eclipse can be a little painful. So I definitely like the running this in Eclipse. So that's pretty much it. I think the slot-based statistics class can be reused in many other projects in the future. It's a very general use case. All we're doing is calculating aggregate statistics of some number over some period of time. I'm thinking maybe like using utility data to monitor the number of volts used over a period of time and alerting for spikes. I'm not 100% sure that this was the best use of Storm for this particular use case. I think it may be a little bit overkill. Since we didn't really need that many threads, there's not a whole lot of data being emitted from these Bitcoin spouts. However, I definitely think it served as a great learning tool to really get to know the nuts and bolts of it. I'm really amazed at how easy it is to make massively parallel applications that are essentially infinitely scalable. It abstracts all of the threading gotchas, and it lets you just get down to writing code. I'm sure we'll be hearing more about real-time analytics, and I'm sure that it'll be a pivotal part of every organization's big data architecture. So what's next? I think there are a lot of ways we can improve upon this project had we had more time. For example, right now it'll poll every 10 seconds. This is not ideal. I think a better method, we would want essentially every trade, we would want to emit a tuple for that. So it really would be real time in that case. We could potentially miss some spikes with 10-second polling. It'd also be good to have some sort of persistence for the statistics. We could write this out, the rolling windows, to Hadoop or Cassandra, and we could view the changes over time. I think it would be really interesting to mine this data and see if we can hook it up to machine learning, like Mahao, so we can try to predict, will the price go up or down today? Is this unusual volatility? What are the expected values? Also, I think if we could connect this to New York Stock Exchange and NASDAQ, essentially any financial security, we can essentially just reuse the code. I mean, every security has a last price, bid, ask, etc. I think another potential use case would be to do automated arbitrage. So we could look at two exchanges and see, are they selling Bitcoin on one exchange and buying on another one? So we can do automated arbitrage, which I think would be pretty fun. Also, in this use case, the alerts are kind of dumb. We just set, is the delta $5? If so, send an email. I think we could really enhance this by maybe having it backed by a database, so alert with these scenarios, and a web UI, or maybe fire off a Nagios alert in that case. So just some housekeeping. The source code is available on GitHub. The key class, the sliding window statistics, it was adapted from the Storm Starter project, the sliding window counter. So essentially what that does is you take a key and then maintain a count of how many times it appeared in that rolling window. So I enhanced that to, instead of just the count, it'll do min, max, average, volatility, etc. A link to the Storm documentation. This is excellent for an open source project. And finally, a link to the Bitcoin exchange API that I used. It made it dead simple to connect to the exchange and emit the data for that.